Now let's solve search insert position. In this problem, we're given a sorted array of distinct integers and a target value. We need to return the index if the target is found in that sorted array, and if not, we need to return the index where it would be if it were inserted in order. And the most important point in this problem is that we must write an algorithm with O log of n runtime complexity. And we'll talk about that in just a moment, but let's go through the examples to make sure the description is clear. So we have this nums array with the numbers 1 through 5, 6 and a target of 5. We need to see if target exists in our array, and if it does, we need to return the index in which it sits. So in this example, target is 5 and it exists in 0, 1, 2. It exists in position 2, so we return 2. In example 2, target 2 does not exist in our nums array, but we know that it should come right after the 1, and 1 is in position 0, so we need to return 1 because that's where the 2 would be, right after position 0. Now, the most straightforward way to solve this problem would be to run a for loop int I equals 0 as long as I is less than nums.length I++, and if nums at I is equal to target, then return I. And if it doesn't exist, in another independent for loop, we can check if the nums at I is greater than target. In that case, that's where our target should be placed, and so we return that I. Now the problem with that solution is that although it runs in a linear runtime complexity, the question requires us to solve it in O log of n. And so with the runtime complexity of O log of n, that's a pretty good hint that we need to solve it using binary search. And now, so that begs the question, what is binary search? Well, when we have a sorted array, one way to find target is to assign an int variable called left, which is the leftmost index of our array, which obviously is 0, and an int variable called right, which is the rightmost index of our array, which would be nums.length minus 1. So in this case, it's 0, 1, 2, 3. And then what we're going to do is we're going to calculate the midpoint of the indices. Let's just say it's 0 plus 3 over 2 for convenience, but it's a bit of a different equation, but it's the same thing. And so we're going to get 3 divided by 2, which is 1.5, but as an int, it's just 1. So our midpoint index is 1, which is 0, 1. So nums at 1 is 3. We're going to take nums at mid and compare it to target. Now, 3 cases may arise from this comparison. Either nums at mid is target, and so we return mid, which would be the index where target exists. And then the other 2 cases is that nums at mid is actually less than target, which would mean that our target actually exists after our mid index. And the second case is that nums at mid is greater than target, which means our target actually exists before the nums at mid or before the mid index. And in that case, we're going to update, well, in either of the last two cases I mentioned, we need to either update the left index or the right index. And to really stress on the importance of binary search, if you recall, I mentioned a way to solve the problem using 2 independent for loops in the beginning that runs at a time complexity of O of n, whereas binary search runs at O log of n. The difference is if we had an array of like 1 million elements with a time complexity of O of n, we're going to check 1 million elements, correct? Because int I is equal to 0, and then we're checking worst case, our target exists in the last index. So we're going to check 1 million elements. With O log of n, we're actually going to check worst case scenario 20 cases, because initially we have an array with pointers at left and right, which are the leftmost index and the rightmost index, and we find the midpoint. And after we compare nums at mid to our target, we're either going to cut our new array to study the left half or the right half. So like from midpoint to the right or from midpoint to the left. And so worst case scenario, we're going to check maximum 20 times. So there's a huge difference between checking 1 million elements and 20 elements max. So let's begin coding now. Like I said, we're going to create a leftmost pointer int left, which is equal to 0. And int right, which is equal to nums.length minus 1. And now what we're going to do is we're going to keep looping while left is less than or equal to right. And now we're going to calculate our midpoint. So if you recall, I mentioned for convenience that our midpoint is going to be equal to left plus right. If you divide that by 2, you're going to get the midpoint. And although that is correct, and we're going to use that concept, we're going to change it just a bit. So what we're going to do is we're going to create an integer called mid or midpoint or whatever, which is not equal to left plus right divided by 2, but actually it's equal to left plus right minus left divided by 2. So why did we do that? That's because in binary search, if we had a really big array, and let's say for example left is equal to 1 billion and right is equal to 1.5 billion, if you add left plus right, you're going to get a value of 2.5 billion. Now the problem is that int can only hold a size of up to 2.15 billion, and so obviously left plus right surpasses that. What's going to happen is that once we surpass about 2.15 billion, Java will wrap the number around and turn it into a negative number, and so our value for mid is going to be garbage. It's going to be useless. So the way to mitigate this is to use this equation instead, which if you expand, you're going to get essentially left plus right divided by 2, which is essentially the same as left plus right divided by 2. But by doing right minus left, you're going to ensure, and then dividing it by 2, you're going to ensure that this number never exceeds 2.15 billion. So now we're going to check if nums at the index mid is equal to target. And if that's the case, then we just need to return mid. Else, if nums at mid is less than target, then our target actually exists from the index of mid plus 1 all the way to the right, and so we need to update our left pointer. So if that's the case, left is going to be equal to mid plus 1. Otherwise, if nums at mid is greater than target, then we need to check the left side of our arrays, or the left half of our array, so left to mid, and we need to update our right. So right would actually be equal to mid minus 1. So in this commented out section, let's explore what these two cases mean. So in the beginning, we have left is equal to 0 and right is equal to nums.length minus 1, which is 5. And so our mid is going to be equal to 0 plus right minus left, which is 5 minus 0, divided by 2, which is 2.5, and that's 2. So we go to index 2, 0, 1, 2. So nums at mid, or nums at 2, is 5. We're going to compare 5 to target. Is 5 equal to target? It's not. Okay. Is nums at mid, so is 5 less than target? Yes. That means that our number actually exists in the second half of our array, and we're going to update left to be mid plus 1, which is 2 plus 1, which is 3. So left, which started at 0, is now actually at index 3, which is here. And we skip this else statement, we go back, we recalculate mid. Mid is now equal to left, which is 3, plus right minus left, so 5 minus 3, which is 2. 2 divided by 2, that's 1. 1 plus 3, that's 4. So in our second half, our midpoint is 8, 0, 1, 2, 3, 4. And once again, we check, is nums at mid equal to target? It's not. Is it less than target? It's not. It's greater than target. So we need to update our right pointer to be mid minus 1, which is index 3. And so we go back to mid. Mid is now equal to left, which is 3, plus right minus left, which is 3 minus 3, divided by 2, doesn't matter, that's 0, left is just 3. So 0, 1, 2, 3, we're looking at 6. Is nums at 3, which is 6, equal to target? It is, so we return 6. And that's the gist of binary search. We keep breaking down the array into halves and finding the midpoint of these halves and comparing the number that we want to our target to see which half we need to explore. So now this addresses the possibility that our target lands on a mid index, even if we recalculate mid. But if target does not exist in our nums array at all and we need to return the index of where it should be placed, all we need to do is return left. So let's submit our code and see if it works. And there we go. So one thing I want to clear up before we wrap up this video is why do we return left in the end? That's because in our while loop, we said left is less than or equal to right. So once we exit this while loop, that means the search range has shrunk to 0 and the algorithm has looked at basically everywhere the target could possibly be. And by that point, right is the index of the last element smaller than the target, and left is the index of the first element greater than or equal to target. And that's exactly where we need to insert our target to keep the array sorted in order. So that was the search insert position problem on LeetCode and an introduction to binary search. I hope you found that video helpful, and thanks for watching.